Today, we're going to be explaining one of the simplest yet most powerful components in electronics, the diode.
A diode is like a one-way street for electricity. It lets current flow in only one direction, from the p-type to the n-type material. The p-type is known as the anode, while the n-type is known as the cathode.
In order to show the functionality of the diode, we decided to create a simple circuit connecting a battery to a diode with an ammeter to measure the current in the circuit. As you can see, the current flows perfectly fine in the following arrangement. However, when the terminals are switched, the current is flowing the other way. Based on the ammeter, one can tell that there is very minuscule current that actually flows. The one-way property happens because of the p-n junction, which forms a depletion region. As electrons and holes recombine near the junction, they leave behind charged ions. This region, with fixed ions but no mobile charge carrier, is called the depletion region because it is depleted of free electrons and holes. No free charge carriers in there, causing it to act like an insulator. However, applying a forward bias, which means positive to the anode, negative to the cathode, will cause the depletion region, or the barriers, to lower and current to flow easily.
On the other hand, applying reverse bias will widen the barrier and block current, so very little current is able to flow. Let's get into what's really going on. In the p-type side, we've got holes, missing electrons. On the n-type side, we've got extra electrons.
Connecting a forward voltage causes electrons from the n side to jump across to fill the holes on the p side. That's how current flows.
This flow depends on carrier concentrations. Here's a key relationship. This equation solves for the hole concentration on the n side of the junction under forward bias. This equation tells you how many holes make it to the n side. The exponential term grows with increased forward voltage, so as V increases, P sub n increases exponentially.
Think of this as the barrier keeping holes on the p side like a hill. When you apply forward voltage, you're lowering the hills, so more holes can cross over. The steeper the slope, the more holes make it to the other side. The equilibrium concentration is when voltage equals 0. Subtracting the equilibrium concentration gives us this equation, which causes it to simplify to this equation.
This same term appears in the famous Shockley diode equation, which gives us the current flowing through an ideal diode.
Here, I0 is the reverse saturation current. Q is the charge of the electron, V is the voltage across the diode, K is the Boltzmann constant, and T is the absolute temperature. We use this equation because in forward bias, the exponential term dominates and lets current flow. However, in reverse bias, current stays tiny, so it just becomes I0. This can be seen through the Shockley model, carrier concentrations and currents. These show the depletion regions over certain concentrations.
However, remember that the Shockley diode equation models an ideal diode. In reality, things can be more complicated. Real diodes have resistance and temperature that can play a large role. As temperature rises, the saturation current, I0, increases, which means that the diode can conduct more current at the same voltage.
When diodes are placed in circuits with other components, like resistors or capacitors, their nonlinear behavior can make circuit analysis tricky. That's why computer simulations are usually used to figure out circuits involving many diodes.
Say you've got diodes in series or in parallel. We can start with the Ohm's law and Kirchhoff's voltage law. For a diode in a loop, V total equals IR plus V diode. You would plug in the Shockley equation for V diode.
Let's look at some applications of diodes. While transistors are usually used for logic gates, diodes can be used as well. An OR gate can be made using two diodes and a resistor and will allow current when at least one of the input currents is turned on.
Here, you can see an AND gate made from two diodes and a resistor, which allows current only when both of the input currents are turned on. Logic gates are the basis of all electronics, and when combined, can create complex systems starting from simple bit addition to functional computers.
And as you can see by this very simple encoder, every single small circuit requires a lot of different diodes and elements. Diodes can be used everywhere and anywhere. Logic gates are used in all computers. This is, for example, a 4-bit adder. Devices such as these are useful throughout all of computing. Diodes can also be used to create a voltage regulator. To do this, a specific diode called a Zener diode is often used. Unlike a regular diode, Zener diodes allow current to flow from the cathode to the anode, or from the negative terminal to the positive terminal, under specific conditions and without completely failing.
Current is allowed to flow through while applying a reverse bias when a specific voltage, called the breakdown voltage, is applied. When this occurs, the voltage across the diode will be equal to its breakdown voltage, even when the voltage applied increases above the breakdown voltage, thus providing a constant voltage source. To better explain what is happening, this circuit diagram will be referenced.
If the breakdown voltage of the Zener diode above is 6 volts, the voltmeter at the right end of the circuit will read 0 volts. In this case, the voltage over the resistor is 5 volts. If the breakdown voltage of the diode is 4 volts, the voltage over the diode as read by the voltmeter would be 4 volts, and thus the voltage over the diode would be 1 volt. Thank you for listening to our presentation.